Picture this. You push a tiny, one-line bug fix to your AWS environment. It seems completely harmless, right? But 2 minutes later, your API starts throwing HTTP 500 errors, your database connections sever, and suddenly your entire production application flatlines. The panic sets in as customer complaints start rolling in, and your pager is going off uncontrollably.
You didn't just deploy a bug, you deployed a disaster. Why did this happen? Because you built a blazing fast CI/CD pipeline, but you completely forgot to build the brakes. You optimized for speed over operational safety.
Section 1. The danger of automation. Why safeguards are critical for the DVA-C02 exam. The core mental model you must adopt right now is this: automation without safeguards is incredibly dangerous. Let me show you exactly how a single bad deployment destroys an application, and more importantly, how good AWS developers engineer operational safety to stop it in its tracks. Think about it like this. CI/CD is essentially a high-speed freight train. Continuous integration compiles your code, and continuous delivery pushes it out to the server. But if that train is carrying a bomb, and there are absolutely no safety checkpoints along the tracks, that bomb goes straight into your live user environment. Without safeguards, the blast radius is 100% of your users. Everyone is impacted.
Now imagine this real-world scenario. You update your AWS Lambda code to expect a brand new JSON payload structure from your front end. You deploy the Lambda function, but you haven't deployed the new front end yet. Or worse, and I'm going to slow down slightly here because this is huge. The new code writes a completely different partition key format to Amazon DynamoDB, but the old front end is still blindly trying to read the old format. You just caused a massive database mismatch issue. Your API is completely broken, and worse, customer data is being corrupted in real time. Just a total nightmare.
Section 2. Manual approval gates. The first line of defense. Listen, this is where people mess up. They naturally think automated deployment means absolutely zero human interaction from start to finish. But let me tell you, that is a dangerous assumption. To protect your system, you must implement an approval gate in AWS CodePipeline. Here's exactly how it works. Before the code ever touches production, the pipeline physically stops and triggers an Amazon SNS notification. A human QA engineer reviews the staging environment, verifies everything is functioning perfectly, and clicks Approve. Only then does the automated deployment proceed. That one single click, it's literally the difference between a safe, boring release and an entire weekend of firefighting. Section 3. Immutable deployment strategies. Preventing live server corruption. But what if the bug slips past QA? If you're using an in-place deployment, meaning AWS Code Deploy is installing the new code directly over the top of the old code right on your live servers, you are in massive trouble. If that deployment fails halfway through, your live server is corrupted. Instead, to truly protect your infrastructure, you absolutely must configure deployment strategies like blue/green, canary, or rolling for your application releases. Let's look at how this works on an EC2 compute platform. In a blue/green deployment, the instances and a deployment group are replaced entirely by a different set of instances. Code Deploy provisions a brand new set of EC2 instances. This is your green environment. It safely installs the new code right there. And the beautiful part? The original blue instances are completely untouched. They are still happily serving your users. Once the green environment is fully verified, the instances in that replacement environment are registered with an elastic load balancing load balancer, causing live traffic to be cleanly rerouted over to them. Think about that for a second. If the new green environment crashes under heavy load, you don't have to panic. You don't have to frantically rewrite code or restore from a backup. You just flip the load balancer straight back to the untouched blue environment. Your recovery time is measured in seconds, not hours. Section 4. Automated monitoring and rollbacks. Building self-healing systems. Now, here's where this gets really interesting. At a certain scale, you don't want to rely on a human to notice the site is down and manually flip that switch. You must rely on sophisticated deployment monitoring and automatic rollbacks. As an AWS developer, you meticulously instrument your code to emit custom metrics to Amazon CloudWatch. You then configure your pipeline to actively watch a specific CloudWatch alarm during the deployment phase. If your API error rate spikes by even 5%, the CloudWatch alarm trips. The pipeline instantly detects this, halts the deployment, and performs application rollbacks by using those existing deployment strategies we just talked about. The system self-heals before your users even realized there was a glitch in the matrix. Section 5. Serverless deployment traps. Navigating environments without EC2 instances. I need you to really watch out for the serverless deployment traps, especially if you're taking the DVA-C02 exam. Imagine this scenario. You're fully serverless. You don't have traditional EC2 instances or application load balancers to easily shift traffic back and forth. So how do you safely deploy an update to a serverless API without risking taking down a live version? Well, you do this by managing environments in individual AWS services. Specifically, you differentiate between development, test, and production right in API Gateway using stages and Lambda aliases. This segregation is absolutely vital. Without it, a single bad push to a monolithic Lambda function immediately brings down your production API. By separating these stages, you create a hard isolation boundary. Your production users are safely hitting one stable stage, while your developers are freely testing breaking changes in a completely different stage without impacting live traffic. Here is how you actually execute it. You publish your new Lambda code as a distinct new version. Then, and I'll slow down slightly here because this is key, you use a Lambda alias with a weighted routing configuration to send 90% of your traffic to the old stable version and only 10% to the new version. This is called a Canary deployment. If the 10% Canary fails, your tiny blast radius means only a small fraction of users are impacted. If it succeeds, you slowly shift the rest of the traffic over time. You combine this by using existing runtime configurations to create dynamic deployments, such as mapping staging variables from API Gateway directly into your Lambda functions. So your production API stage reliably points to the stable alias, and your dev API stage safely points to the latest untested code. Section 6. 3 Rapid Takeaways. Essential CI/CD operational safety. Let's lock this down before we wrap up this explainer. 3 rapid takeaways you really need to internalize. Number 1, automation without safeguards is extremely dangerous. Always use orchestrated workflows with manual approval gates to prevent unverified code from ever reaching production. Number 2, use immutable deployment strategies like blue/green or Canary to drastically reduce your blast radius and enable instant, safe application rollbacks. And number 3, diligently instrument your code to emit custom metrics so your infrastructure can automatically detect deployment failures and self-heal in real time without human intervention. I'll leave you with one final warning. A deployment is not successful just because the code compiled successfully on your machine. A deployment is only successful if you can mathematically prove the live application is healthy and you have a one-click strategy to revert it if it is not. So take a hard look at your own AWS environment today. If your next deployment fails entirely, are you recovering in 5 seconds, or are you recovering in 5 hours?